This video is going to cover the topic of tangent graphs and then cotangent graphs. Now, the first thing I have for you to try and get us along the right track is the table that we started off with for sine and cosine. I just used all of the values from the unit, all the angle values from the unit circle, and I have sine of those values and cosine of those values. So we know the sine graph looks like this. Starts off, when we look at the parent function, starts off at 0, goes up to pi over 2 and 1. Notice that this up here is 2. And then pi, 3 pi over 2, 2 pi. So this is something you've seen multiple times. Then we have the cosine graph, which starts at 1, 0, pi, 3 pi over 2, and then 2 pi. So these tables are really valuable because they give you this clear curve, just like any other function. But I wanted you guys to see those again before looking at the tangent table. And we're going to go over most of these values. We're actually going to create this table by hand, just like we did in class. But I wanted you to see the graph to just get a general idea that something different is happening here. Something very different. This graph is this weird, like, snake repeated over and over again. So let me see, I have, oh no, where's my blank screen? I have a blank screen somewhere around here. Let me pull that back up and then we can make this table and then talk about the points and why it does this strange shape. So let me pause my video real quick while I figure that out. Okay, the visual that you're seeing here is just the basic setup that I wanted to use to go over all of this. I have just our standard triangle that we use to create everything else, theta, our opposite or our sine, and adjacent or our cosine, and then 1 for our radius, because we're still working on the unit circle to create this first graph of tangent. So sine of 0, meaning my angle here is 0. If you remember the unit circle, it's this point right here. Sine, we're going to go through all the sine values first, then all the cosine values, then we're going to put them together as opposite and adjacent. So sine here, that's my height, that's 0. Sine of pi over 6, that is the short length, because if you'll remember, the same triangle rotated one more time, or adjusted one more time, would be the tall length for my height. So short and tall. So my short is 1/2. My tall is square. Oh, not there yet. There's my undo button. Okay, the tall is square root of 3 over 2. Then we have that middle one, that pi over 4, that's square root of 2 over 2. The 90, or pi over 2, that is the highest value that I can get for sine, which is 1. Then 2 pi over 3, that gets, that's that height again, the tall longer length, square root of 3 over 2. Then pi over 4, that's that length in the middle again, right here. That's square root of 2 over 2. 5 pi over 6, that's that shorter one, which it just didn't do it proportionally. That's 1/2. And then pi, it's this angle right here, that is 0 again. Now the only reason that I'm only stopping at pi is just because I couldn't fit it all in the page. Maybe see if I can zoom out. Yeah, if I zoomed out, I could do more, but then I'd have to write smaller, or just the proportions wouldn't work. So I'm just going to leave it like this, and you guys can just put together what happens on the other side. So then let's go with cosine. So let me erase this so that I can do the cosine lengths again. Got my circle. We're starting off at 0, and this time we're talking about our horizontal. Well, that's 1 over pi over 6, pi over 4, pi over 3, pi over 2. So pi over 6, that's the longer of these two lengths. So that's square root of 3 over 2. Pi over 4, that's square root of 2 over 2. This is the shorter length, so that's 1/2. And then this here is 0, because I'm not moving left or right at all. Then I'm actually getting a negative 1/2, negative square root of 2 over 2, and negative square root of 3 over 2. And then finally when I get back to, it's there, when I get back to pi, I am going a negative 1 in the x direction. So all I want to do for this next column of the table is create my opposite over my adjacent, because we know that tangent of theta is the opposite over the adjacent, and we really haven't talked very much about tangent, and so that's why I think this would be valuable for us to do the entire table and really consider what happens here. So my opposite, and it's kind of crammed in here, my opposite is 0 over 1. Well, that's just going to equal 0. My opposite here, I'm going to stagger it so that I can fit more in. 1/2 over square root of 3 over 2. I don't really like the way that looks, so I'm going to write that in. Let's see, this is scissors. I think I can take all of that. Yep. Okay. Sorry about that. So 1/2 over square root of 3 over 2. I'm going to multiply this by the reciprocal. I'm going to multiply the top by the reciprocal here, the flip of it. And I think we actually did this already, but I'm going to go through all of the steps again to refresh for anybody who might need that. I multiply across, and that gets me this, but 2 over 2, those factor out to equal 1, so I have 1 over square root of 3. But I actually cannot leave it this way. We all know at this point that we need to rationalize that denominator, because otherwise we have a square root in the denominator, and just mathematically that doesn't work for us. So this will simplify to square root of 3 over 3. That's for pi over 6. Then pi over 4, I have square root of 2 over 2, and that's my opposite, over square root of 2 over 2. Well, we should recognize that that is simply 1, because those cancel out. Pi over 3, square root of 3 over 2, over 1/2. I'm going to multiply my numerator by my reciprocal, the flip of this fraction. These guys cancel out, and so I just simply get square root of 3. I'm actually going to pause the video and draw in some lines here. Well, yeah, I'm not going to pause because I'm lazy. That's an extra click. Did I do that wrong? Yeah, that shouldn't be up there. There we go. So that's the problem. Okay, let me pause the video. Give me just a second. Okay, done. Now, my next one, I have 1 over 0. That is not an acceptable value. That's undefined. Then I'm actually back to some values that I saw before. I have square root of 3 over 2 over negative 1 over 1/2, but this time it's negative, so the value is not going to change. It's going to stay square root of 3, but it's a negative now because I have positive divided by negative. Then square root of 2 over 2 all over, square root of 2 over 2, and this one's a negative. That's a negative 1. Then 1/2 over negative square root of 3 over 2. We already did that up here, so that's square root of 3 over 3, and that's a negative. And then 0 over negative 1. That's just, I was going to put negative 0. What am I thinking? That is just 0. So let's take a look at this table again. Let me put them next to each other actually. And whoops, how can I get this over? Zoom out, no. There we go. So we got this table, and we got this table here. which is pretty similar. We have sine, cosine, although I now have opposite over adjacent. This is just my calculations table. Hopefully that won't confuse you guys too much. So if we look at what we have matching here, so I'm going to move this over, and I'm going to slide so that way you can see the matching part a little bit better. And I'm going to actually write a little bit on here. We've got 0 and 0, that matches. We have 0.577, so we need to know that square root of 3 over 3 equals 0.577. We have 1, and then square root of 3 is 1.732, and then undefined, and then negative 1.732, negative 1, negative 0.577, and notice I'm approximating, and then 0, and then if you look at the next value, it's 0.577, 1, 1.732. So we have 0.577, we have 1, 1.732, undefined, negative, 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 and then 2 pi, the end of the unit circle, meaning we made our full rotation, happens again. So these values, starting here or starting here, those are completely the same values. Like this is just a repeat. And we've talked about this before actually. So let's minimize this, maximize this. We talked about the fact that sine, just a second, starting from 0 to 2 pi, we can repeat this over and over again. So this value, these values are a repeat of these values. We also said that cosine works the same way. So from 0 to 2 pi, that's a repeat of negative 2 pi to 0, and so on and so forth. So for sine and cosine, we have a repeat of 2 pi, a repeat of 2 pi, but then for tangent, if we look at this, we start at 0, and then we get to pi. We start at 0 and we go up a bunch of positive values all the way to undefined, and then start with some negative values up to 0 again, and then we start that process again. So this right here is repeated here, here, and here. Our tangent value actually repeats every pi, which hopefully you're seeing in these values here and in the table. So that's something that makes a difference in your calculations. You need less tangent calculations than you do sine and cosine. So let's talk about what's actually happening at, where is it? Let's go with a different color. At this point here. Hopefully from Algebra 2 you remember this type of line that I'm drawing in. And we'll talk about it in just a second once I'm finished. Let me pause the video while I finish this part. Take me just a second. Okay. Quick warning. I have a dog asleep behind me, so if you are hearing any weird noises in the background, that is him. Anyway, so these lines here, if you'll remember from Algebra 2, back in high school when you're talking about a topic called conic sections, you're talking here about a line called an asymptote. An asymptote is if part of the graph where this is an imaginary line, it doesn't actually exist, this dotted line, but it marks off where the graph will never has values or has a point there. And that's for any y value. That x is just is not allowed. And if you'll remember from like exponential functions or um, rational functions from other topics, you can actually have asymptotes in the horizontal way too, so you can have them like this. But that's not what we're talking about here. We're just talking about vertical asymptotes. So this this graph does not have values in a lot of places. And so that really makes the domain difficult for us because we don't have a straight domain, a simple domain like cosine, where we have a point in every y value. We have a point in every x value for sine as well. That's not the case. So let's talk about why we have those asymptotes and where they're coming from. So if we look at sine and tangent, the asymptotes come where sine is 1. That doesn't really help us out. That I don't see any connection there. But if I look at let's try looking at cosine and the asymptotes. If you'll notice, this comes where cosine is 0. And so hopefully you're figuring out why you have an asymptote in these spots. Why you cannot touch the graph. The graph cannot be touched or cannot have a point here at all where cosine is 0. Well, if you think about it, I closed the tab with all the calculations, didn't I? Yeah, so you guys can't see those calculations anymore. But if you think about what we were doing before with those, where I had, you know, I was doing the opposite over the adjacent. Here, my opposite is 1, and my adjacent is 0. We said that was undefined. If I cannot have a point exist there, well then, of course, my graph cannot exist in any of these points. And so actually it does not matter at all where sine is. That does not really, well, it's not that it doesn't matter, but it doesn't change the asymptotes at all. Where cosine asymptotes sit, that is where our tangent, where cosine is 0, that's where we have tangent asymptotes. So that's something that you guys need to be aware of, and that's the whole reason that our graph has this really strange shape. And we'll talk about cotangent in a little bit as well. But so this hopefully clarifies why you have quite a funny graph. So let's talk about our domain of tangent. Let's see. Let me clear this. Let's just put tangent of x. So there's our graph. And let's say I wanted to do an equation, x equals pi over 2. And I'm going to make this a dotted line, or dashed line, so that you can see that that's a, I can't duplicate it. That's fine. So you can see that that's an asymptote. X equals 3 pi over 2. X equals negative pi over 2. And so I've got the graph actually doing these for me. And those of you who have Texas Instruments calculators, sometimes the calculators will actually make one solid line that looks like this, and it includes these vertical lines. That's just because the calculator is connecting that top point up there to the bottom point down here, but it's not actually, this vertical line is not actually part of the graph. Just be aware of that. So let me make these all dashed. Okay. So those are our asymptotes, and if you'll notice, they're all in very specific places. They're in pi over 2 fractions, and they're spread out by a value of, let's see, they're spread out by a value of pi. Because if I say negative pi over 2 plus pi, that gets me pi over 2, plus pi, that gets me 3 pi over 2. Just like before when I said that the period of each tangent is pi, the period of the asymptotes is pi as well, or the gap between them. Sorry, I'm just going to pause the video really quickly so I can do something. Okay, so let's talk about, now that we've seen the basic parent form of the function, let's talk about the transformations using A, B, C, and D, which we've talked about and used before. Now I've got these sliders here, and I'm going to just adjust each one, and then we'll discuss how that changes the graph. And this time, because we have this whole extra consideration, these asymptotes, I do want you to think about what that would mean for the graph, or what the graph changes mean for the asymptotes. So if I change A, I want you to think for a quick second, will that change where my asymptotes sit? You know that A represents our amplitude, and it represents the vertical stretch or compression of the graph. Does that change where my graph is undefined? Does that change those values? So take a second. Anytime I tell you guys to take a second, by the way, I would recommend just pausing if you need to think about it or to try and figure it out. So anyway, if I'm changing A, let's see, my graph is getting more and more steep. Now you may think that it's becoming a straight line. I know this is a lot to look at, but take a notice, those are still curved lines. It's just that it's really steep and it's hard to see that when you're zoomed in. So let's go back to A as 1. And so you can see the curve in there. Let's get back in here. Whoops. All right, we were about, sorry, I just don't want to have more on the graph than we need. We're about here. Okay, so A doesn't look like it's making the graph shift in a way that changes the asymptotes. And when I make A a fraction less than 1, notice that that curve, that steepness changes. But again, my asymptotes still look like they work. And let's, just for the sake of showing again what happens when we have negative A, because we know that that's important to consider, our graph reflects. Hopefully you guys remember that it reflects across the y-axis. Still does the same thing though. Still changes the steepness. So I'm going to put A back down at 1. My asymptotes have not been affected by A. It's good to know. Then let's go to B. Oh, you know what? I should give you guys a second. Remember that B changes our horizontal stretch or compression, and it is a reflection across the x-axis. You know, the x-axis? Yes. No. No, it should be a reflection across the y-axis. So B is the stretch and compression and a reflection. Will that change our vertical asymptotes? So if I change B to be a larger number, notice that my period is changing. The amount of times that I have that curve, that general shape, has increased quite a bit as B increases. So you know what? I want to go ahead and say that it does change my graph, or my asymptotes. If B changes, look at that. I've got part of this graph covering this asymptote. We know that that's not possible. We know that there's a point where cosine is 0. And so that changes the way that this looks quite a bit. So I'm going to put B back to 1, and we'll come back to that. Then let's talk about C. Hopefully we recognize, or we can take a guess. I want you guys to remember, C is my horizontal translation, left or right. So I want you to think about what happens to my graph as C increases, and what happens to my graph as C decreases. Does that change the asymptote? So as C increases, my graph, so C shifts to the right as C increases, and so we definitely have to consider how it changes our asymptotes. I'm going to put back, and then it shifts to the left as C decreases. Okay, I'll go back to 1. And then finally, Wait. Oh, sorry, C is 0. Starts off as 0. And then finally D. I'm going to take a second, think about again, will this affect my asymptotes? Okay, hopefully you paused and thought about it. This looks funny. That looks like my graph is just like bending. But we know that's not actually what D does to the graph. So let's zoom out so we can see what's actually happening. And keep your eyes on the way the graph moves in here. It's really hard to see. It's like a let's see, how can I show this to you? You know what? If I put a domain restriction, I should be able to show it. So let me pause it and change the way the graph is written a little bit. Give me a second. Okay, this should be about where we were at. Okay, all I've done is I have cut off the rest of the graph just so that you guys can kind of see clear what's happening, and hopefully you'll be able to see what D is doing now that you have those endpoints. All D does, and all D ever does for any type of function, is a vertical shift. So as D decreases, it shifts further down. As D increases, it shifts further up. The graph is not changing shape. It's not bending in some weird way. Hopefully we're all clear on that, but I just wanted to be a little extra, I don't know, extra clear. Okay, so we need to think about, let me take off this domain restriction now. You know what, you guys can keep that. It might be helpful. Okay, so we need to think about how can we change the formulas for our asymptotes? How can we make those shift with the graph? Because, you know, it's important to have that. And I'm only going to have one so that way, right now, so that way there's no confusion and you're only focusing on one line. So right now, when B is 1, we know that B changes it and we know that C changes it. So those need to show up in here. So let's just try tossing it. Let's go with B is 2. When B is 2, I have a lot more. I have pi over 2, I have pi, 3 pi over 2. So if I try to toss in, well, so let me try tossing in a B. B times that. No. B plus that. No, that didn't work. So I think it would be really valuable for you guys if you took the time to type out, go to desmos.com. Write that out for y'all. Desmos.com/calculator. Oh, if I put slash, it makes it a division because I'm typing in here. But desmos.com calculator, and then I want you to type in all the stuff that you see here and try and explore around and see if you can't figure out something that B does. And I'm going to pause and I'm going to do the same thing. I'm going to play around with it a little bit and I'll let you guys see what I'm doing. So I have B times that, and then let's plus C. Let's see. So the plus C shouldn't change it at all because C is 0 right now. Let's do 1 over B. Did that work? I'll do times. Let's see. Well, earlier I had 3 pi over 2. So let's do 1 over B again. And then the plus C isn't, like I said, isn't changing anything right now. That looks like that might be where my graph, and I mean, I can't tell you guys I don't know the formula. I don't know how this works because I know this formula, but all I did was I took the B and I was like, well, maybe if I multiply it, that'll change it. So, well, let me do the opposite of that. Just showing some explorations here. Let me make this a dotted line. Okay, and it worked from what I can tell. So let me change B and look at that. Because I used B instead of a specific number, it changes with the graph. Okay, so now let me see. Let me see what it looks like whenever I don't change C, when I don't include C on here. So they don't change, they don't shift when my graph shifts. So let me go back to 0. And now let me include C. Oops, not equals, plus. Oops, I'm using the wrong part of the keyboard. Okay. Look at that. Now it works. Those asymptotes move with my graph. So if you just take a look. And so now I can actually have my graph do, it's going to look kind of funny, but my amplitude is changing. My amplitude is changing quite a bit. And my period is changing. And my horizontal part is changing. And my vertical part is changing. And none of it, and I can guarantee you that that asymptote never crosses the graph. This is a lot happening right now. Let me turn this all off. Look, see, I turned it off. Oh, well, that's because I have my domain restriction. If I added this back in, ooh, that's that's hard to look at. But hopefully you see that what I did was I analyzed what I was looking at, and I created my graph from there. And so look at that. If I scroll up, I will never see this asymptote cross. And so I told you guys, I don't expect you to memorize tons of stuff, but you are expected to be able to figure out exactly where the asymptotes are on any graph that I give you. Any tangent and any cotangent. So let's talk about those real quick. Any cotangent graph as well. That is ugly. Let me pause it and change my parameters. Okay, you now have a screen showing you cotangent effects. And without confusing you, I want to remind you, here's tangent of x. So again, cotangent, tangent. They should look very familiar. And if you'll remember, we said that cotangent is just the inverse of tangent. So let me write that out. Let me use my little tablet in just a second. So we have that tangent of x equals sine of x over cosine of x. And we know that cotangent of x equals 1 over tangent of x. Well, 1 over tangent of x is 1 over sine of x over cosine of x. And that is saying 1 times the flip, or the reciprocal. So cotangent of x equals cosine of x over sine of x. So before, the determining factor in our asymptotes and what made the graph so strange is the fact that we had a cosine of x in the denominator. Now with cotangent of x, sine of x is in our denominator, and that is the determining factor in a lot of important parts of the graph. So I'm going to take this one off. We're looking at cotangent of x, and just like before, if you look at sine, the part of the graph where it goes to negative infinity all the way up to positive infinity out of nowhere, for cosine, it's just 1. That's the y value. That doesn't change anything. That's not anything special. But for sine, that is where sine of x is 0. And that makes sense. Anytime sine of x is 0, we have that denominator is 0. Not possible, so cotangent of x would be undefined, and that's why we have some asymptotes happening again. So let's, again, add in the parameters. So let's add in a, b times x minus c, whoops, plus d. Okay, I'm going to put sliders in for all of these. And let's see, let's put this to 0, because that's where we start off, with no shift in vertical or horizontal direction. This is our graph. And then let me see, x equals 0. That should be, yeah, that's a vertical line at the 0 point. X equals pi, that's a vertical line there. x equals negative pi. Those are my asymptotes. Let me make them look as such. Here, here, and this one needs to be dotted. Oh, I didn't. Yeah, they're all dotted lines. Okay, so our asymptotes are very similar to our asymptotes before. I want you guys to then take a guess. I want you to pause the video. You should know which parameters create the shift in the asymptotes, or the need to shift. And I want to ask you, let's see, what is the equation for any vertical asymptote of cotangent of x? And so you're going to pause the video, and I want you to try and write the equation very similarly to the equation that we used for the tangent asymptotes. So I'm going to pause the video, and then I'll tell you when I'm, well, no, just going to give you a few seconds, and I'll type it in. Alright, I actually did pause it just to do some settings here. So I have, hopefully you came up with the equation 1 over b. This time you could put 0 plus c, or times 0 plus c, or you could put pi, works as well. Now, this is to adjust for any transformations in the graph that we might have. So if b changes, this is what it should look like. I'm actually going to put pi in here so you can see the adjustment and the transformation a little bit better. So you can see it moves with it. And then c, it will move it with it as well. This is for one line though. If you'll notice, I don't have the equations for all of them anymore. I only have one equation. And so your textbook actually talks about this, and it's very similar to something else we've talked about before, which is, let's actually clear all of this. No, should we? Let's clear these three for sure. And this. So you come up with the equation for that, but I want to increase this. I want to have more than one line. So what you would do is, let's see, yeah, so we have x equals, let's go, yeah, x equals 1 over b times pi plus c, but we're going to multiply this by, no, you know what, that's not right. We're going to add k pi again. Where's the slider for k? It should give me a slider for it, and it's not. Give me a second. Let me try and figure out what the formatting is for this website. Okay, the formatting on this website is actually going to be a little difficult to show this, but if you had, so I thought, well, let's just skip the formatting part of it and just consider what you would do to calculate it. So if I wanted one more, I thought, well, let me see. My period should be pi. Well, actually, it's not. In this case, the period is different because I've changed it. Let's actually make it back to 1. Let's see. I'm gonna zoom out here. There we go. So in this case, the period is pi. Let's see, pi times 1 over b. So if it changes every time, yeah. So you are still adding the same amount again, 1 over b pi. It's just you're changing it by a factor of k. And k won't show up as a specific number variable. Let's go with e. Yeah, so it won't give me any new sliders for some reason. So you just need to know that just like coterminal angles, if I wanted to add another one, I'd just do the same thing, 1 over b times pi. And that gives me another one. And then if I But if I wanted to find a different one, so notice the red line, let me do that times 2, times 3, times -2. So that formula there that you're seeing is how you would have more than one show up. Well, sort of. It's just that you'd have to repeat it. You'd find those coterminal asymptotes at the same angle, just with a full rotation. Don't overthink that too much. If you have one and you have the graph, you can find another one just by finding the period. So in this case, my period should be 1. So plus 1 over b times pi. That's another one. And then times 2, times 3, times 4. So it's just a matter of adding more to the rotation, just like coterminal angles are. Now, this might seem like a lot to toss at you, but don't worry, I'm not actually expecting you to memorize these formulas. We have a very straightforward way that we can work through this, all of these calculations. And it is, there we go. It is actually very simple to do any transformed graph if you know the parent function. So you have to know the sine x shape, the cosine x shape, the tangent x shape. And then we haven't really talked, well, here's cotangent of x. We talked about that one. We haven't talked, though, about cosecant of x or secant of x. So you got a lot of stuff going on here. Let's take off everything else except for sine and cosecant. That's kind of weird. Cosecant of x is a funny shape, but it's not something that we need to worry too much about right now. And then, because that's the next topic. And then secant of x is a funny shape as well. Same thing, just shifted. So let's talk about how to just shift any of these three functions. And we'll kind of flip back and forth. Okay, so you're going to bear with me because it's been a while since I've taught this topic, but what we have here is an equation with quite a bit of variable or parameters changing it. A lot of transformations happening. We have a, b, but this is weird because I know that I showed you guys we have, and don't worry, I actually know what's happening. I'm just trying to put it in a nice way. We had the function that look like this. But what I'm seeing here doesn't have a whole separate x minus c in there. That means I'm going to have to change the way the graph is written in just a second. I'll just put a and d down first because I know those. So I need to get 1/3 x minus pi over 6 to look like this, because right now it just looks like that. I need to get that separated from b. So that means I need to factor out 1/3. It has to be 1/3 because if I don't, then I'm leaving something behind with the x. The only thing that I can factor out is all of it. And that might seem kind of challenging to factor out 1/3 from pi over 6. Factoring, though, just means that you're dividing. So let's see. That's the same as what we've done multiple times in this video, which is multiplying by the reciprocal. So we have pi over 3 pi over 6, which hopefully we recognize as pi over 2. So minus pi over 2. And that tells me now that b is 1/3 and c is pi over 2. So I now have all of, hopefully, so if you need that written down to see how to factor this out in those cases, then you need to pause the video because I'm about to erase all of that. Oh, I didn't take the scissors. Okay, so anyway, sorry, I should have paused the video for that too. Anyway, we have now what A, B, C, and D are. And this might look to you like, well, how do I go from here? But the easiest thing is to create your own graph. Let's see. with no parameters right now. So let's just go up to, that's about right. And let's just come out here. And I don't know what any of these numbers actually are. So I'm going to create those numbers. The first thing I'm going to do is my y values. I want this center line to be the center of my cosine graph. And if you'll remember, cosine graph starts at 1, goes to 0, looks like this. And it's so important that you know these 5 very important 5 key points. This is usually 0, 1. You have pi over 2, 0, sorry. Then you have pi, negative 1, 3 pi over 2, 0, and then 2 pi, 1. So these are usually your values, but those are going to shift. And I want this center line to be based on my vertical shift. So if my graph did a vertical shift up 1, then instead of being at at y equals 0, this line here, my y value is now going to be 1. And my amplitude is a negative 2. Well, I'm going to not look at the negative right now. We need to make a note of that. So remember, A is negative. Okay? So either way, my amplitude is 2. That means that my graph goes up 2 and down 2 total. So I'm at 1. If I go up 2 more, then that takes me to 3. And if I go down 2, here's 0 and here's negative 1. I now have my vertical shift and my amplitude taken care of here. Those are both already considered. But I also need to consider the x values. And let me erase some things here so they're not confusing, they're not tossed in. Let's see, let's get that out of the way. I'm just showing you the x values that we start off with, because those are going to shift and those are going to be stretched. So let's talk about the shift first. Sorry, I'll get that out of the way. The first thing is that our graph shifted horizontally pi over 2. That means that I'm starting off at pi over 2 instead of 0. And my b, that tells me how long my period is, but there's a formula for this if you'll remember. The formula that I told you guys for the period is 2 pi over b. So in this case, 2 pi over, let's just do 1 over 3, which is what b is. Oh, sorry. I'm not used to this whiteboard. Anyway, which is 2 pi over 1 times 3 over 1, because I do the reciprocal, which gives me 6 pi. So my graph stretches out over to 6 pi here. Well, it's a distance, a period of 6 pi, but it already started off at pi over 2. So let's think about that. Let me erase some things. No, you know what? Yeah, it should be fine. So I start off at pi over 2, and I'm adding to get up to 6 pi more. So let's see. That would be pi over 2 plus 12 pi over 2, and I'm just changing the 6 so it has a matching denominator. So that tells me that I'm at 13 pi over 2, because this is 1. 1 over 2 plus 12 over 2 is 13 over 2. So this is parentheses 13 pi over 2. That's my x value there. So comma right here. And so that's my ending point. I don't know what the y value is yet. I'll figure that out in a little bit. And I've got a lot more work to do to find those key points. So let's get some stuff out of the way here. Ugh, I'm taking some time here. Sorry about that. Well, I mean, you guys would see some of that happening in the classroom too anyway. So we have our starting point of pi over 2 and our ending point of 13 pi over 2. But if you'll remember, there are 5 points. There's that middle and these two in between the end points and the middle. So I need 4 equal segments. So segment 1, 2, 3, 4. So I need to have, let's see, 1 point, 2 points, 3 points in between for 1, 2, 3, 4 segments. So I need to figure out, well, I'm breaking it up into 4 equal parts. Let me figure out, well, I mean, how long is each of those equal parts? So let's see. How can I do that? How can I break up this distance into 4 parts? Hopefully you guys are seeing what I'm doing here. Oh, I am simply saying I need to find how much to add to pi over 2. Let's see. So 13 pi over 2 minus pi over 2. Oh, that's right. That's just 6 pi. That's all I had here. That's how much that's the distance between them. So if I actually take my period, erase it. So this is the period divided by 4. That'll get me all my key points. And hopefully you guys are seeing that setting up the margins of this graph, that's the easiest part. The key points are really what makes this difficult. I mean, it's going to be calculations no matter which way you do this. But anyways, we have 6 pi over 4, which will simplify to 3 pi over 2. So this next point will be pi over 2 plus 3 pi over 2. Let's see, well that's 4 pi over 2. Again, plus 3 pi over 2. That's 7 pi over 2. Again, plus 3 pi over 2. And that should be, uh-oh, what did I do wrong? Oh, I didn't do anything wrong. I started off with pi over 2 down here. Whoops. Yeah, that's fine, whatever. So I started off with my starting point, and I added 3 pi over 2. That's what happened here. And then that gives me 4 pi over 2. And then I added 3 pi over 2. That gives me 7 pi over 2. And then I add 3 pi over 2. That gets me, sorry, that's my dog snoring. And that gets me 10 pi over 2. And then 10 pi over 2. I add 3 pi over 2. And that will get me 13 pi over 2, which is down here. So that's that added there. So I'm going to recap all this in just a second, but just so you guys are aware, all I've done is I said starting point, key point here, whoops, key point, key point, key point, key point. Those are my 5 key points. They all come from breaking up this graph into 4. You will do that every single time, okay? So I'm going to erase a bunch of this stuff to make more space. Let's erase this. Erase this. And I wrote these really large. Hopefully you guys are okay with that. So let's figure out our y values. Cosine usually starts up at the top, goes down to the middle, the very bottom, here, and here. So usually my graph would look like this. That is my transformed graph. I'm done. Let's see. So my y value here is 3. My y value here is 0. Here is let's see, 7 pi over 2 negative 1. This is 0 again, and then this is 3 again. I've got all 5 of my key points, this is written down there, already done. Like, the hardest part was adding a bunch of fractions. But I didn't remember that a was a negative, so I gotta fix that. Let's now recap everything. We had a lot of stuff there. So we started off, whoops, with y equals negative 2 cosine of 1/3 x minus pi over 6 plus 1, which we rewrote as negative 2 cosine of 1/3 x minus pi over 2 plus 1. We figured out what a was. B, C, and D. And then we said, okay, well, let's use all of these values to create our graph. Let's see, 1, 2, 3, 4. Yeah, that should be fine. And let's see, 1, 2, 3, 4, 5. Let's see. And sorry, I say the same things all the time. Okay, let's see. Yeah, sorry. Anyway, that's another one I say all the time. So we started off with a vertical shift. So we started off using D to find our vertical shift. And then we used A to find our height of the graph. And then we used C to find our starting point. And I'm going to write those points out. Pi over 2. And then we added 3 pi over 2. I've erased everything, so now I've got to think it through again. I know it ends up at 13 pi over 2. Let's see, it's 6 pi over 4. Yeah, so we added 3 pi over 2, which takes us to 4 pi over 2, plus 3 is 7 pi over 2, plus 3 is 10 pi over 2. And notice that I just did it kind of in my head here, but that's definitely not something what I want you to do. So you'll use B and the period to find your key points and to find your endpoints. So we have all of these key points. I'm not going to label them on the graph though, I just got them down here. So I know I've used all 4 of these to find my key points and my parameters. Let's see, so this is pi over 2, 13 pi over 2. And because a was negative, I'm actually going to start off down here. Hopefully you can figure out that I'm doing my reflections. Did I do too many points when I drew this out? I did. I drew out 5 over here and I forgot about my starting point. That's unnecessary. There's my graph. Transformed. So let's see, negative 1, 0, 3, 0, negative 1. And that's my graph using 4 different values, including a pi value. It's pretty complex stuff, broken down into a few simple steps. So what I'm going to do is I'm going to do, how much time have I, this has been an hour. I want to do a little bit more, a couple more examples, hopefully, if I can cram that in terms of time, just so that way you guys have a bunch of, as many examples as possible, because I know that this is hard to see just out of nowhere like this. Let's see what your textbook has for examples. Let's see, that's the wrong textbook. This is chapter 2. see, sketch at least one cycle of the graph. Let's actually do a tangent graph, because sine and cosine are so similar. Oh, this one doesn't have all the parameters. That's fine. We can do it. So I would take a note of what we did here. See, so D is our horizontal line. A was our top and bottom lines. C was our starting point, or starting X. And then the B in the period, that's the ending point and the key points. And then you fill in your graph. So let's clear this and do a new example. Okay, let's go with f of x equals, let's do another sine or cosine first. -1/2 sine of x minus pi over 2, and then let's go with plus 3. So a, -1/2. I would recommend after I've put in, so I'd recommend you pause at each step and try it out first before you see what I do. Otherwise, you are not getting yourself the best opportunity to test yourself and your understanding of what we're doing. B is 1. C is again pi over 2 actually, and then D is 3. Now, I'm going to do a rough sketch. Don't care how long it is. I know I'm going to have 4 sections, and I know I'm going to have an upper and lower bound. And I'm going to start with D, my vertical shift. I start off at 3 here. My next y value is going to be up 1/2, so 3.5, and down 1/2, 2.5. I'm going to make a note, a negative, so that I can remember that later. And then my starting point is pi over 2. Let's see. I'm going to use the period, which is 2 pi over b, which is 2 pi over 1. Alright, so the period is 2 pi. That's helpful. So I then make my key points. I have pi over 2. And I end 2 pi later. Well, I don't know my ending point actually, but I do know how to find my key points. First, they will be 4 equal sizes, or equal spaces. So I'm going to take the period 2 pi divided by 4, which is pi over 2, right? Yeah. So I will, let's see, so this is pi over 2 plus pi over 2. What's this one? That's 2 pi over 2. And it's easier if you don't simplify, because if you simplify, then your denominators aren't going to match. So that's my next point. And so then it's 2 pi over 2 plus pi over 2. That's, sorry, I blanked for a second. There's a 1 there. So that's 3 pi over 2. 3 pi over 2 plus pi over 2. This is 4 pi over 2. Let's see, so that's 1, 2, 3, 4. And then I need 5. So 4 pi over 2 plus pi over 2. That is 5 pi over 2. So let's see. Pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and then 5 pi over 2. I now have all of my points that I could need. Let's see. Anything else? So let's see. My sine graph, I'll remind myself, starts here, goes up, back down, further down. Yep, there's my sine graph. But I have to make this memory, or this note, a is negative, so it's going to be the flip of that. Still starts here, but instead of going up, it goes down, back to the middle, all the way to the top, and back to the middle. All right. So if I take a look at the y values for these points, let me erase some stuff here. I have pi over 2, and my y value is 0. That's where I started off. 2 pi over 2, or which is just pi, and if you're working in my math lab, you have to remember that. 2 pi over, or 2.5. Oops, I said 0 is my y value. It's not 0, it's 3. In this case, I'll give you guys an excuse for not correcting me, because of course you can't. Not in this case, anyway. 3 pi over 2. Just fill these in real quick. Alright, 3 pi over 2 is the middle point. That is again back at 3. 4 pi over 2. Jimmy, stop snoring. Hey, you're making noise. Sorry. My fourth point is at 3.5. And then my fifth point is back at 3. So I have all my points. I have the general shape of my graph. Good to go. Let's do one more example. And then, actually, I haven't had time to go over identifying from a graph. We'll look at that too. Anyway, so let me clear this. I would take note of anything you like before I erase it. So pause it if you need to. All right, I'm going to clear it now. Clear the page, and let's do one more example. Oh yeah, we need to do a tangent example. So let's go with y equals tangent of 3x minus 2. Okay, now we have a equals 1, because there's no 0 there. If there was 0, this part wouldn't exist. It would just be 0. And let's see, b equals 3. C, there's nothing being added or subtracted, so it's 0. And then d is negative 2. That c is going to help us out. It's going to make things a little bit easier. First thing I do, sketch, d, negative 2, c. Get my top and bottom. A is 1, so I'm going to be up 1, negative 1, and down 1 at negative 3. I start at 0, and b is 3. That does not mean I get to say that I put a 3 here. I need to remember, or we all need to remember, that my period is 2 pi over b, which is 2 pi over 3. That's how far this is going to go, or that's how far this is, 2 pi over 3. And in this case, that's pretty nice because we started off with 0, so we're going to end up at 2 pi over 3. When you look at these functions, if you have b and c values that you need to consider, that's when it's hardest to do. If you only have one, it's easier to calculate these things because it follows pretty standard set. Anyway, so I need my key points. I need to find out these three values, or these, those three x values. So I'm at 0, and then 2 pi over 3. So I need to break that up into 4 sections, which is 2 pi over 3 times 4 over 1, because it's just over 1. Do that reciprocal. So it gets me, this is ugly. Did I do that right? No, I didn't flip that number. That's wrong. Sorry. So I have 1 over 4. That's why. So I have 2 pi over 12. I'm not going to simplify. I'm just going to leave it the way it is. It's just easier, honestly. So then I have, let's see, this next point should be 0 plus 2 pi over 12, which is 2 pi over 12. And then you just add this a couple more times. And hopefully you see, when I don't simplify the denominator, Oh, it's so much easier. And then just to check, I can say um, this should equal 6 pi over 12 plus 2 pi over 12. And since that's simplified, it's going to be a little bit different. 8 pi over 12. And if I simplify that, let's see, I divide that by 4. It gives me 2. And I divide that by 4, and it gives me 3. All right, I did all of these correctly. So let's see, 0, 2 pi over 12, 4 pi 12, and 6 pi over 12. We know that's 8 pi over 12. Anyway, now I have tangent. So that's going to be a little bit different. We need to consider what is the parent function of tangent over the course of one period. So I know it starts off at 0 because that's sine over cosine, and sine of 0 is 0. And then remember last time when I did the sine graph real quick and the cosine graphs real quick, I need to do that for tangent as well. Let's see. And then, let's see, so 0 pi over 2 pi, 3 pi over 2, and then 2 pi. It's supposed to be pi right there. Remember that I'm just doing the parent function to give me an idea of the graph. Okay. Anyway, so pi over 2. Sine of pi over 2 is 1, and cosine of pi over 2 is 0, so this is where I have the undefined. And then, so my graph went up here. And then at pi, my graph, let's see, so sine of pi is 0 and cosine of pi is 1. Okay, 3 pi over 2, that's where sine is 1, cosine is 0. So that's another undefined. And then at 2 pi, that's where sine again is 0 and I have 1. So my graph looks like this, looks like this. So I'm going to do the same thing here. Because I've already done my key points, this is the really beautiful thing about this setup, is that I don't need to think anymore about what's actually happening. I just transfer these special points. See, so I know that there's an asymptote here, and there's an asymptote here. I know that the graph has zeros at these points, and then looks like this. That's my tangent graph. The way that you work through this does not change no matter which function you're doing. The only difference between the trigs is this parent function. This is where you'll have to remember the different values. So I don't expect you to have those memorized, and on previous tests I have provided the parent function for students, just so you guys are aware. I am coming up on 1 hour and 15 minutes, which is how much time we have in class. I don't want to take any more time than that, but I am going to just pull this to the side and show you guys really quickly what all this looks like on a graph. So we have tangent of 3x minus 2. Why am I not seeing it? Oh, I see why, because it was unclicked. Ooh, that's a lot. That's ugly to look at. Sorry about that. So that's not matching what I have here. It doesn't match this beautiful little graph we've created. So I'm actually going to use these graph settings to change my margins. We start off at 0, and then we end up at 2 pi over 3, and I'm just typing in 2 pi over 3. That's why I like Desmos, because you can do that kind of thing. Our y value starts at negative 3, and our y value ends at negative 1. Let's see, and then this step thing, I still haven't exactly figured out the steps in Desmos. It's 2 pi over 12 is how we did our steps, meaning our major intervals. Let's see. And then my y value steps, let's just go with 1. Okay. So this is kind of hard to see because this is something that's a little pet peeve of mine. You don't have any margins on this graph, so it does match, but we have a little bit of extra around it, a little bit of window. So I'm going to add a little bit. Let's just add 0.25. Actually, subtract 0.25 here. So see how it gave a little extra? And then let's add 0.25 here. Gave another little extra over there. My y values. There we go. Let's take this off the image. So this should match. And it does. Hopefully you guys can tell. We have our -2 median line. -2 median line. We have our asymptotes at, it's not giving me, oh there it is, it's up at the top. Pi over 6, well that doesn't match what I have. Oh, that's right. Remember, if you're in my math lab or if you're in some sort of digital tool, it will not leave the fraction in that format. I'm leaving it that way just because it's easier to type in. So 2 over 12 simplifies to pi over 6. 4 pi over 12 simplifies to pi over 3. 6 pi over 12, pi over 2, and then 2 pi over 3. That's where it ends up back at the center again. So hopefully you guys see and you can test this out on your own time when you're transforming any graph. All of this work that we did is to get you to the point to understand what this graph actually is, oops, and what all of these guys do to the graph. And now you can adjust it however you want it. So that's where we were at right there, down at the -2 line. This is what the graph actually looks like. If I wanted to compare this to tangent of x, this is what you took the graph from this red one to the black one. You did that. Or earlier we had, oh, I can't remember anymore. It was -2 cosine of 1/3 x minus pi over 6, I think. And then, oof, what was the other number? I think I've already I closed that. I don't remember what the y value was. I think it was +1. So anyway, this was what your graph was. Your graph started off as cosine of x, and you created, by doing these adjustments, that new graph. It won't look new to you. It will still look just like this blue line because it's like you zoomed in on the new graph. You zoomed in so that it would fit and look just like that. So this margin change makes it easier for you to work with all of the new values that we've been working on. Oh my god, I just realized that my window stops right here for what records. I sure hope that it recorded the top of the work I did with you. Let me pause the video and look. I just realized I can't look unless I end the video. So let's hope it worked. I'm going to post this either which way, and if you guys have questions, let me know. This was supposed to be taught as if I was basically teaching the lesson in person to you guys. So wherever you have questions, you pause, make a note, and then if you want, send me an email with all of the timestamps. So, I had a question at 2 minutes and 36 seconds. Why did you do this? If you're not clear about what you're confused about, if you tell me I don't understand the video, which I get all the time from students in all of my classes, including my junior level courses. Don't worry, this is not calling anybody out. I get this all the time. I don't know what you're saying in the videos. Well, you need to be clearer. I made an hour and 15-minute video. Give me more detail. So if you tell me that, I can respond to your questions, and this way we are not losing any content time. And I look forward to hearing how much you understood, and I'll see you guys hopefully on Wednesday.